Welcome everyone, welcome on class 4. In today's lesson we will be discussing about three-dimensional airflow around an airplane, span-wise flow and wingtip vortices. As we can see here, it has about 57 questions. We will pick around 30 again, and let's get started. Induced drag is the result of boundary layer separation on the aft portion of the wing, downwash generated by the wingtip vortices, propeller slipstream over the wing, and aerodynamic interaction between airplane parts. What is induced drag? Induced drag is caused by the wingtip vortices that are created over here. The energy that gives the wingtip vortices the energy to rotate, this energy is taken from our aircraft, and this is why it's called induced drag. Also, that part right here, behind the trailing edge, you have the downward component which is called downwash. So induced drag is created by the wingtip vortices. So the correct answer is downwash generated by the wingtip vortices. So wingtip vortices, in summary, create the downwash. Moreover, wingtip vortices are existent along the wall, along the span of the cord at every point. But the stronger of the wingtip vortices are located at the wingtip. What is the effect of increasing wing aspect ratio on induced drag? Here I've put a summary. Give me a sec. I've put a summary on the upper left side. What happens with higher aspect ratio, with higher angle of attack, with higher weight or speed? In general, the size and strength of wingtip vortices depends on pressure differential, speed, and cord length. Moreover, in this section, in this topic, we will use extensively this formula. Coefficient of drag induced equals with coefficient of lift squared divided by P, which is a constant, and aspect ratio. I shouldn't have done that, but it's okay. So, what is the effect of increasing wing aspect ratio on induced drag? Let me fix this first. But you will see we don't even need this summary because everything can come up from this formula. What is the effect of increasing wing aspect ratio on induced drag? Let's go to our formula and see. If we increase aspect ratio, if aspect ratio goes up, coefficient of drag induced goes down. So it's pretty straightforward. It reduces because the effect of wingtip vortices is reduced. It's the only one that says it reduces, so the correct answer is A. Which of these statements about induced drag are correct or incorrect? Induced drag increases as angle of attack increases. If we increase angle of attack, coefficient of lift increases. So CDI, coefficient of drag induced, is proportional with coefficient of lift. So question number 1 is correct, and at a constant load factor, induced drag increases with increasing airplane mass. First of all, I will show here the first one is correct, and for a greater mass, we need greater lift, which means higher induced drag. Both of them are correct. Number C, correct and correct. Which of these statements about the strength of wingtip vortices are correct or incorrect? Assuming no flow separation, the strength of wingtip vortices increase as the angle of attack decrease. This is incorrect according to our formula. And the strength of wingtip vortices decrease as the aspect ratio decreases. Both of them are incorrect according to this formula. So we're looking for incorrect and incorrect. The correct answer is D. Which statement about the effect on drag of fitting external tip tanks to the wing of an airplane is correct? Parasite drag increases. Of course, parasite drag increases because we increase and the skin friction drag and the form drag because we increase the area, we increase the shape. Of course, wingtip tanks have an aerodynamic design, but this doesn't change the fact that parasite drag increases. And induced drag increases. No, induced drag decreases because most of the wingtip tanks are aerodynamically designed to act as winglets. What does the winglets do? The winglets act like a wall as a barrier, preventing the wingtip vortices going from the lower surface to the upper surface. So in that case, if we have a wingtip tank, at the tip, it will have the same effect. It will act as a wall, reducing the wingtip vortices. So, parasite drag increases, correct. Induced drag decreases, incorrect. Incorrect and incorrect. Given a constant load factor, which of these statements about the variation of induced drag with changes of speed and mass are correct and incorrect? When speed increases, induced drag decreases. This is correct, because to have the same load factor means we want to remain straight and level. So when we increase the speed, coefficient of lift goes down, induced drag goes down. We see here on the summary. Lower angle of attack, lower induced drag. When mass increases, induced drag increases, because we need more lift, and more lift creates more drag. So when speed increases, induced drag decreases, correct. And when mass increases, induced drag increases, correct. Both of them are correct, so the correct answer is D. Flap extension at constant indicated airspeed while maintaining straight and level flight will increase the maximum lift coefficient and the drag, stall speed, lift and the drag, lift coefficient and the drag. Extending the flaps will increase our CL max, but also will increase the drag, because we increase the area. Given a constant load factor, just a reminder, load factor is this type, N equals lift divided by weight, and when we are straight and level, this equals to 1. Given a constant load factor, which of these statements about the variation of induced drag with changes of speed and mass are correct or incorrect? When speed decreases, induced drag decreases. This is incorrect. When speed decreases, we increase our coefficient of lift, because we increase our angle of attack to remain straight and level, so induced drag increases. The first one is incorrect. And when mass decreases, induced drag decreases. The second one is correct. So incorrect and correct. The correct answer is A. Assuming no compressibility effects, induced drag at constant indicated airspeed is affected by engine thrust, airplane mass, outside air temperature, and altitude. As we have seen, it is affected by the airplane mass induced drag. Let's see, not by the engine thrust, not by the altitude, by the airplane mass. The heavier the airplane, the heavier the induced drag, because we need more lift to support the aircraft. Which of these statements about the strength of wingtip vortices are correct or incorrect? Assuming no flow separation, the strength of wingtip vortices increase as the angle of attack increases. This is correct. according to our formula. Coefficient of drag induced is proportional to coefficient of lift squared. So correct. And the strength of wingtip vortices decrease as the aspect ratio increases. Also correct. Proportional and inversely proportional. This increases, coefficient of drag induced increases. Aspect ratio increases, coefficient of drag induced decreases. Both of them are correct, pretty straightforward. Given a constant load factor, which of these statements about the variation of induced drag with changes of speed and mass are correct or incorrect? When speed decreases, induced drag decreases. When speed decreases, induced drag will increase. So for the first one is obviously incorrect. And when mass decreases, induced mass increases. Both of them are incorrect. We have seen similar questions a lot of times. So incorrect and incorrect. The correct answer is D. Given a constant load factor, which of these statements about the variation of induced drag with changes of speed and mass are correct or incorrect? When speed increases, induced drag increases. Incorrect. Because when speed increases, in order to remain straight and level, we have to lower our angle of attack to lower our coefficient of lift, so induced drag decreases. And when mass increases, induced drag increases. This is correct. The first one we said incorrect and correct. Oh, let me see if it has here the total drag curve. No. Okay. So we said when speed increases, induced drag must decrease, so incorrect. And the second one is correct. Incorrect, correct. Moreover, you can see at this point have the coefficient of drag. Oops. And the speed as speed increases, this drag curve, as speed increases, induced drag, this is the induced drag curve, induced, as speed increases, induced drag decreases, and as speed increases, parasite drag increases. So at this point, that these two drag curves connect, we have the V minimum drag, and we sum up with the total drag curve, which is something like this. What's the effect of winglets on the drag of the wing? Winglets, as we mentioned earlier, decrease the induced drag because they act as a barrier from the flow of the air from the lower surface to go to the upper surface and create wingtip vortices. So they decrease winglets on the drag of the wing, increase parasite drag, decrease in crucial. So due to their shape, they increase the parasite drag because they are a solid object, but they decrease induced drag. What's the effect on induced drag of an increase in aspect ratio? An increase in aspect ratio will decrease induced drag. So induced drag decreases because the effect of tip vortices decreases. Which of these statements about the strength of wingtip vortices are correct or incorrect? Assuming no flow separation, the strength of wingtip vortices decreases as the angle of attack decreases. This is correct. And the strength of wingtip vortices increases as the aspect ratio increases. And this is incorrect. Correct and incorrect. The correct answer is A. Induced drag is created by the span-wise flow. This is the key word you must look for. Span-wise flow pattern resulting in tip vortices. Which of the following are means to reduce induced drag? Increasing the wing thickness, camber and span, decreasing the taper ratio, increasing the root chord and the sweep angle, increasing the aspect ratio and wing twist, adding winglets, obviously this is the correct one, and decreasing the wingspan, increasing the approach speed and takeoff weight. Obviously this is the correct answer. Describe the airflow with regards to the induced drag. Okay, from the top to the bottom via the tip, from the bottom to the top via the trailing edge. Okay. Air wants always, according to pressure gradient, to go from high pressure we have here to low pressure. So it goes that way and wants to go to the upper surface. So it wants to go from the lower surface and it moves like that on the lower surface and on the upper surface, because the pressure here is less. In the upper surface it moves like that. So the correct answer is from the bottom to the top via the tip. Maybe from the top to the bottom, no. From the bottom to the top via the trailing, no. From the bottom to the top via the tip. The value of the induced drag of an airplane in straight and level flight at a constant mass. Excuse me. So let's get back on track. The value of the induced drag of an airplane in straight and level flight at a constant mass varies linearly with 1 divided by v squared, okay, it varies linearly. Do we still have the graph? No. The graph of the induced drag, if you remember, we drew it earlier. As we increase the speed, induced drag. Here we have the drag. As we increase our speed, induced drag decreases. So it's v squared. Yeah, it's v squared. Okay. So don't do the same mistake like me. Don't go too fast. What is the sequence of decreasing the wings upwards? Increase induced drag since effective angle of attack increases. Increase induced drag since angle of attack increase. Decrease induced drag since effective angle of attack increases. And increase and decrease induced drag since decrease of angle of attack. So the stronger the up was or the down was, these two work together. For example, the stronger the down was, the stronger the up was. Every action has a reaction. So what's the consequence of decreasing the wings upwards? If we decrease the wing upwards by reducing, for example, the angle of attack, reduce the downwards. When we have downwards, this is the relative airflow. We have something which is called effective airflow. And the bigger the downwards, the steeper the effective airflow. So the steeper the airflow, the steeper the induced angle of attack, and the less the effective angle of attack. Maybe I'll draw it over here. So we have here an airfoil, the relative airflow, the effective airflow, no, this angle of attack alpha over here between the effective airflow and the relative airflow is called angle of attack induced, and this alpha right here between the effective airflow and the curved line is called alpha effective. So in theory, lift is proportional to the acts at 90 degrees to the effective airflow lift, and the bigger and steeper the effective airflow, the this is completely wrong, the more swept back will be the reaction force. And this angle right here is angle of attack, is the same angle of attack induced. So by decreasing the upwash, we decrease the downwash, we decrease the induced angle of attack, we decrease induced drag, and the effective angle of attack increases. Because you can see here, I'll find a picture. The induced drag will get smaller and smaller, and the angle of attack effective will increase. This is the correct answer. Which of these statements about the strength of wingtip vortices are correct or incorrect? Assuming no flow separation, the strength of wingtip vortices increases as the angle of attack decreases. No, incorrect. Assuming no flow separation, the strength of wingtip vortices increases. No. We return to this formula again. Reducing angle of attack, reducing coefficient of lift, reducing induced drag. Incorrect. The strength of wingtip vortices increases as the aspect ratio decreases. This is correct. Incorrect and correct. Which of the following are most effective at reducing induced drag? High aspect ratio and removal of winglets. Of course, we want winglets to reduce induced drag. Lower aspect ratio and flaps, lower aspect ratio and wing fences, higher aspect ratio and winglets. We have explained the reason. Given a constant load factor, which means we fly straight and level, Which of these statements about the variation of induced drag with changes of speed and mass are correct or incorrect? When speed decreases, induced drag increases. This is incorrect because we increase our angle of attack, we increase our coefficient of lift. So correct. And when mass decreases, induced drag increase. Incorrect. When mass decreases, induced drag decreases. So correct and incorrect, which is correct. Okay. A. Which of these statements about the strength of wingtip vortices are correct or incorrect? Assuming no flow separation, the strength of wingtip vortices decreases as the angle of attack decreases. This is correct. And the strength of wingtip vortices decreases as the aspect ratio decreases. Incorrect, because if the aspect ratio goes down, this goes up. So as the strength decreases, correct and incorrect. Given a constant load factor, which of these statements is correct about the variation of induced drag with changes of speed and mass are correct and incorrect? When speed increases, induced drag decreases. Yes, because in order to remain straight and level, we will lower angle of attack, we will lower our coefficient of lift, and induced drag decreases. So number one is correct. We can also bring in mind how the graph of the induced drag acts with speed, and when mass increases, induced drag increases. So the second one is correct. First one is correct, second one is incorrect. The correct answer is D. The induced angle of attack is a result of a large logar angle of attack in two-dimensional flow, downwards due to tip vortices, change in direction of flow due to the effective angle of attack, downwards due to flow separation, downwards due to tip vortices. I hope I haven't erased this. It's due to the downwards. That's why we introduced the angle of attack induced. I will get used to it, so I hope and my graphs get better. So it's downwards due to tip vortices. In straight and level flight, the spanwise flow on an unswept wing is from the lower surface via the trailing edge to the upper wing surface, lower surface to the upper surface via the wing tip. Obviously, this is the correct answer. Let's see the rest of them. Upper surface via the trailing edge to the lower wing surface. No, it goes like that. Lower surface to the upper surface via the wingtip. The figure shows a polar diagram of coefficient of lift versus coefficient of drag, extending which of the following devices will cause the line to move from position 1 to position 2. So, coefficient of lift to coefficient of drag, okay, extending which devices? Flaps, landing gear, lift dampers, and slats. We have an increase in the maximum ratio, so it must be the lift dampers, I suppose, because we have a huge decrease here. Yeah, let's see the explanation. But as you can see, we had a huge decrease in our ratio. Let's see the explanation. Lift dampers such as wing spoilers reduce lift. Okay. Yeah. Yes, it was the only logical answer, because all the others will move the first graph to another way. An aircraft is following a medium range jet transport aircraft. What is the first action the light aircraft should perform in case he flies into the vortices produced by the wingtips of the jet aircraft? Bank to the right, start a descent, back to the left, or start a climb. The wingtip vortices have a downward component and expand about up to 1000 feet below the aircraft. So the only logical question is to start a climb so to avoid them. Correct. Assuming no flow separation, the strength of wingtip vortices increases as the angle of attack decreases. Assuming no flow separation, the strength of wingtip vortices increases as the angle of attack decreases. This is incorrect. And the strength of wingtip vortices increases as the expectation decreases. Incorrect, and both of them are incorrect. So it wasn't as much difficult. Most of the time, for most of the times, we use just one formula, which is this. Okay, here we have a summary. Don't act fast and do the same mistake. Some things are pretty straightforward. When you are trying to explain a lot of things, you may be confused, but this was obviously the correct answer. I hope you found this video helpful, and see you in lesson 5.